recording now. So the session is being recorded, and I'm going to be sharing a screen, and Erica, so I'm going to be asking you if you're seeing what I want you to be seeing. Let's see, and so you should be seeing an unquiz.
It's up there.
Great, thank you. Now I'm going to say a couple of remarks about the unquiz, and then I'm going to launch it. This is a harder problem than you may have done before, but I think it's an excellent problem to go through. So it's harder computationally, and in fact, this doesn't have special triangles in it, but I think it's useful for us to talk about that. And given the amount of computation here, and again, some of you might say, "Oh, I finished it in 1 minute or something," but I think this might take you a while. But anyway, you're to evaluate this, and you're to evaluate it, using the tools we have and things like that. I am warning you that as you go along, this might be a problem where you would find yourself reaching for a calculator. Okay, so we're starting right now. I'm giving you 10 minutes-ish to do that, and I'll basically call us together. So everybody is working on this now. Okay, so please give it a go. Ericus, can you hear me?
I can.
Thank you. Okay, I'm going to, just put a pin in this, and we will talk through this. Again, if you solved it, congratulations. If you made some progress, that that was good too. And again, the end quizzes are opportunities for you to figure out how are you doing. Are you caught up and things like that, or you need to do a little more work or whatever. Do you want to go to GSGs or whatever? But it's a non-threatening thing. You are getting some credit for doing this, so that's that's a good thing. But the actual assessment here on a unquiz is you're really doing the assessment yourself. Okay, so anyway, we're going to then go through the solution to this problem. And I'm just going to talk, just looking at this problem, I'm going to tell you some of the things that run through my mind. And again, you don't have to think about the same way, but some things that hit me directly. One thing is that this is a definite integral, so the answer should be a number at the end of the problem. So it's not a family of functions. And so that's one thing that I understand right away. Another thing that I lock onto is this thing underneath the square root is like a squared plus u squared. Now, you might say, oh no, 2 isn't a perfect square. Well, I know that, but this is the square root of 2 squared, and the square root of 2 is a number, so I can think about this as being a squared plus u squared. So that motivates doing a tangent substitution. And again, this problem is complicated enough that you don't know if that will completely work or not, but you can kind of say, oh, there's a way going forward. And already I kind of glanced at this, and this wasn't an obvious use substitution of another way. So one of my techniques is I'm going to say that's what I'm going to do. So I will kind of know that at the start of this problem. Okay, so we will jump in. Now I do not have to draw a triangle for this one, because the only time you really have to draw a triangle is if it's an indefinite integral. But it's not a bad thing to draw a triangle, so I'm just going to have, I am sketching the triangle. And so again, what we were saying is that this is this is a squared plus u squared, but the substitution I'm going to be doing, the u squared, if I take the square root of this, I'm going to get 3z. So I'm saying 3z equals the tangent, equals the square root of 2, because that's what a is here, times the tangent of theta. So if I solve for z, z is equal to the square root of 3, the square root of 2 rather, over 3 times tangent of theta. But tangent of theta, though, is equal to, and so it is going to be, the tangent is going to be 3z over the square root of 2. So if I were drawing a triangle, I would put theta here, and the tangent is the opposite over the adjacent. So this is 3z over the square root of 2. And then I know the two legs of the right triangle, so I can compute the other one, and this is the square root of 9z squared plus 2, which you have here. So I'm thinking, okay, that this substitution might really make sense. And so we're going to go through it. Now I do need to figure out what dz is. I'll figure out what dz is from this expression. I need to substitute things in. And one of the other things that's going to happen is, and I told you this, when I'm doing a definite integral, and if I change the variable to theta, I have to have my limits in terms of theta. And I'm probably not going to, and I really don't want to say waste my time, but I'm not going to invest my time in reversing the substitution to go through if I don't have to. The number's going to be what? The number's going to be. Okay, so we have this this stuff, and we'll continue with the solution. Okay, now, So the square root, as we've done before, the square root of 2 plus 9z squared with the substitution I'm doing of, the substitution I'm doing, this is going to be the square root of 2 plus 2 tangent squared theta. I'll factor the square root of 2 out, and then I have 1 plus tangent squared theta. But 1 plus tangent squared theta is known to be the secant squared of theta. And the square root of the secant squared of theta, of course, would be the absolute value of the secant theta. But it will turn out in this problem, and actually it really is the absolute value. And so you have to be mindful of what your range of integration is. It turns out conveniently that here the secant theta is going to be positive in the whole story. And we have to be mindful of our units as well. So, and the substitution we're using is this one, that z is equal to the square root of 2 over 3 tan theta. And that means tan theta is equal to 3 over the square root of 2z. So you see, that's what I'm doing here. So I'll say, well, what are the limits if I'm going to be doing theta? So if z equals 1, we say, well, 1 is equal to this, and so that means tan theta is equal to 3 over the square root of 2. Now, this is where, excuse me, this problem starts getting real, because the special triangles don't have tangents where the tangents are 3 over the square root of 2. This is a real-world problem, and so you will end up using your calculator to figure out what this is. But if you know that the tangent of theta is that, you will start saying, what is the inverse tangent of theta? And if you plug this into your calculator, with your calculator set on radians, because when you're doing calculus, you have your calculator set on radians, you will get that z equal 1 corresponds to theta being, and they could have said approximately, but it's 1.1303, and this is generally accurate enough for something. Now, this isn't what's going to happen on a high stakes assessment because you're not using calculators. But here you can say, yeah, that's something, and that's in the first quadrant. Similarly, z equal 4, you say, well, 4 is equal to this business. And so I can solve for tan theta, it's this, and that says that this is 1.4535 radians. Now, all of these things are in the first quadrant, and all trig functions are positive in the first quadrant. So this absolute value we're just going to drop. But the absolute value is really there. Okay, now I have to deal with dz. And dz, then, from z from the first page, is going to be the square root of 2 over 3 times the secant squared of theta. Okay, so that's what we've got going on, and we're prepared to substitute in and see if good things happen. Okay, so here is the original problem that we were working with, and now here's the substitutions. So this is what dz became, is this business over here including d theta. This square root of 2 plus 9 z squared became this, which is square root of 2 secant theta. Don't need the absolute values. And I'm taking z, which was the square root of 2 over 3 tan theta. I'm raising that to the 5th power. And so I get this thing raised to the 5th power, and this raised to the 5th power, and 2 is 2. And these are my new limits of integration. So that's what I've got going on here. Now, there's a constant here, there's a constant here, and there's a constant here. And you can jerk all those constants out exactly, and you get, and this is exact so far, the exact constant that you will be pulling out is 16 times the square root of 2 over 729. Well, some of my students would say, Jim, that's the ugliest number I've ever seen in my life. But I would remind them that there are no ugly numbers, just like there are no ugly babies. But then let's see what is left. Well, I have the tangent to the 5th, and then here is secant squared, and this is secant 1. So I have tangent to the 5th theta and secant cubed theta. Now this is an integral that we studied in a previous lecture. So And again, I'm not being critical of anybody, but you ought to say, oh yeah, I know how to do this one. And this is one where you're going to strip out because both of them are odd. You're going to strip off a tangent theta and a secant theta. So I'm going to strip that off. And when we strip that off, that means we're committing to doing this integral by making everything into secants. And so that's kind of where we're going. Okay. All right. So here is the tangent theta, secant theta that we stripped off with the d theta. So that's good. And this is the commitment to make everything into a secant theta. Now I did have secant cubed, but one of them I put here. So this is secant squared of theta. And then I had tangent to the fourth after I pulled this one off, but that is going to be tangent squared whole squared. And the tangent squared is known to be the secant squared theta minus 1. So this is what I'm going to be squaring. And so now I'm prepared to do a u substitution. And I'm going to let u equal the secant theta. And I already have du here. Now, I'm making another u substitution, though. So that means that you see up here my limits were theta, so that was fine. But here my limits are going to be u. So I have to change variables again. So not only do I have to do the u substitution, but I have to be mindful of my limits. Now, thankfully, the constant doesn't change at all. It's still out here. But the way you're going to do this is you're going to say, well, when theta is this lower limit, what is the secant of theta? That's a calculator thing. It ends up being this number when you plug it into your calculator. And the upper limit is going to be, this is the upper limit, so what is the secant of that? You plug this into your calculator. And by the way, now I have no idea what calculators you guys are packing, but chances are your calculator doesn't have secant on it. And so the secant is the reciprocal of the cosine, so you have to do it that way too. So there's actually a lot for you to practice on this problem that's useful for you as engineers. Okay, but now we've done all that. I still have to expand this. So this becomes u to the fourth minus 2u squared plus 1. And then I have to distribute the u squared through there. So I get u to the sixth minus 2u to the fourth plus u squared. There's quite a bit of algebra there, but we do it. And we have that, and we've got numbers and things like that. So now it's just a task of integrating. So I'm going to add 1 to the exponent and divide by the new exponent. It's going to be u to the 7th over 7. This is going to be the 2 just sits there. The minus 2 just sits there. I add 1 to the exponent, divide by the new exponent. I get u to the 5th over 5. And here I add 1 to the exponent and divide by the new exponent. I get this. And then I plug these numbers in and multiply by that. And this is a calculator thing that happened here. So we got an answer. This was a pretty good problem. This covered a lot of the things that we've been talking about. So I think this is a good unquiz. Now what I'm going to do right now is, and Ericus, I probably said this, but you're watching the chat, so in case somebody is struggling with their technology today and they can't speak out a question. If somebody asks a question in the chat, if you could be mindful of that as well, that would be wonderful. Okay, so I'm going to count to 10 Mississippi to see if anybody has questions about this. And it's really the whole problem. Okay, I hit 10 Mississippi. No one brought any questions, so I hope that means that everybody says, no, I'm good with what happened here. The discussion was presentation was decent, and yeah, I mean I hope you think this was quite a problem. I actually do. Your questions are always welcome, but I'm moving on because no one brought up anything. Okay, so we're going into the Cockpit Commentary, And down here, I will, at the end of this chart, I will poll for questions in case there's, oh, I don't know, other kinds of general questions that students might have. But I'm going to talk a little bit in this cockpit commentary. This is the end of the COD week. I will tell you that this is not the last day of the week that I'm going to do math. I do math every day, and so does Jesse Hayes Carver. And you should and can as well. But this is the last day we will have class like this. We will not meet again until Monday of next week. And so, I'm actually looking forward to that. Today, I'm going to try to adhere to our normal protocol. We're going to work for 75 minutes or so. That means around 12:15, we will be taking a break. And then we'll take a 10-minute break, and then we'll reconvene. And the second leg of the course will be shorter than the first. It'll be 50 minutes. But if you add those things together, you do get the 125 minutes of quality education that you're paying for. Now, there was a student that asked a question yesterday in class. And I remember it was in Calc 2, certainly. But I didn't remember if it was in this VCM or the other VCM. And again, I was not rude with the student, but we were basically focusing on one thing, and it ended up kind of being a Calculus 1 question. And I promised the student, and I'm very careful about what I promise because I don't like to make promises and then not keep them. So I promised the student that I would address that question. And I was hoping to make a video addressing that question, but I won't go into the detail, but that didn't work out. So I am going to address that student question here, just in case that student is in here and attending today. So I will be talking about that student question, and it's a Calc 1 thing, but it might be a question that some of you had. So and it's not horrible to sometimes review Calc 1, although that's not what we're about. We're about studying Calculus 2. Just from the cockpit, I'm saying, yeah, when I look at things, when we're 1/4 of the way in to the course, I think we're on course and we're on schedule, and we're probably moving about at our cruising altitude and speed. So it's good. The next chart I'm going to show you was kind of our plan, but you can see from the syllabus where we are and stuff like that, and it's working out good. Or working, I guess I should say working out well. Anyway, or at least according to the plan, we're on course and on schedule. I did have a chat. Actually, I had 2 chats. I talked to Jesse Hayes Carver last night on the phone for very late, but I talked for him for quite a while. And I also ended up talking with him face to face today. He is getting a lot of traffic from my linear algebra course, which is really great. But he says he's not getting as much traffic as he would have expected or maybe would have hoped. So if you haven't stopped in with the GSG, I thought for a nanosecond about giving extra credit, and I said, no, I'm not going to do that. But I said, well, maybe if I bought some cookies. So I did buy some cookies, and this is today only, but there are cookies in the 2232 GSG today. And you can come for the cookies, and you're certainly welcome to stay for the quality instruction. Actually, Jesse is a fully certified instructor, and I think he's a wonderful resource for us. We're blessed to have him. I'm going to continue to work this weekend and do things, so you should stay tuned to your announcements and emails, and keep your seat belts buckled and tray tables stowed, because I'm likely to do some math, and I do have an LSA. I was going to make a video about it, didn't get a chance, and so, but gee, with time when I don't have to teach, maybe I will make the video. And so there might be an LSA popping out. Another thing that might be popping out is some additional, I'm going to call it administrative detail about the midterm. Now, it's not going to say, oh, this is exactly what's on the midterm. That's not what I'm prepared to do yet. But we do want to think administratively about, how we're going to pull all that off. And so stay tuned. Okay. The rest of, we are going to cover some new material today. we're going to finish off the trigonometric substitution thing that we were doing, and we will begin talking about partial fractions. Now, I call this part one, and I've taught this course many times. I know about partial fractions, and I suppose I could, and I'm going to use the word naively, assume that everybody remembers how to do partial fraction decomposition. I have learned that students often don't remember that, and so we're going to do that. And we're probably not going to finish the chapter on partial fractions today, and it's not a chapter, it's a thing. I don't know, section of the book, unit maybe. But we'll get into it a bit, and it will all be good. And I do know where I got to with your sister class, and I may have to do some synchronization or something like that, and that's all good too. Okay, so having said all that, I'm going to pause, and I'm opening it up for questions, and this is kind of general questions. I'm not saying, this example that we just did, do you have a question? This is a, it's open questions here. I will count to 10 Mississippi. If someone asks a question, I'll restart my count. Okay, so I'm starting to count right now. And Ericus, you can still hear me, yes?
I can.
Thank you. And if he can, I'm assuming everybody can. Okay, so I'm counting now.
But I also had a question about the guided study groups, because I remember the first week you sent out like a schedule basically for when it happens. So is there a schedule somewhere where like it happens every day?
Well, and hold on for a second, because I am going to answer your question, but I have a way I think I want to answer your question. Now, I am sharing my screen with you, so I think I can get away with this. And I loaded you up into Chrome, so I am going to Firefox, and I'm going to go to, I'm just talking so I can keep track of where I am. I'm going to Blackboard. I'm logging into Blackboard again. Now I'm coming from a different browser, but I'm showing you something different, and I didn't want to get screwed up from Collaborate Ultra. And if I was good at that, I probably could do it in the same thing, but I'm going to Blackboard, and I am answering your question. Okay, so, and the password is and so if I typed correctly, and I did apparently, this is good. And I'm going to go to your class, and I'm going to look at your announcements. Okay, now, and one of the things I do, and I think I probably told you this before, but one of the things I do, and I think it's a good thing to do, that's the reason I keep doing it, is when I send you an email, I create an announcement, and I don't erase the announcements. So basically, this is a reverse journal of the class. Okay, so I'm going through, and I am trying to answer your question, but here are the guided study groups. Okay, now today is Thursday. Okay, and I did go to 2232, didn't I? I'm going to have to talk to Jesse about this, because I think this is not good. Where are we? Here, okay. Okay, so this is the guided study group, whoever asked that question. And so it's there in your Blackboard, so you can go there. And here's the way I guess Jesse Hayes Carver has done this. Some of these are Zoom, and some of them are in person and things like that. Now, the nice thing is Jesse does have some availability every day. But Jesse is a busy guy, and he has to schedule this. They have to schedule rooms, so it's kind of it is kind of awkward. And I do know when I teach 2232. So on Tuesday, in person, in this room in the Learning Commons, you can anybody can go to this GSG, but this is the Tuesday day, and this is in person. This is face to face, so that's good. And either of my Calculus 2 classes could attend this. And I'm not saying that everybody can. I'm just saying, hey, our class isn't meeting then. Okay, so that is good, I suppose. Now on Wednesday, he has one online session from 11 a.m. to 12 p.m. And that's one that you guys on Wednesday, well, I don't say you couldn't go to that. You certainly could, but that overlaps with our class time. So that's not, so on Tuesday, anybody could go. On this day, it's really your sister class is the only one who can go and not be skipping this class. And I don't grade on attendance. Go wherever it works best for you. But this is via Zoom, okay? And that is on Wednesday. And I'm going to tell you that my sister, not my sister, your sister class could do this without skipping class. You guys can't. But on Wednesday, there's also an opportunity via Zoom when you guys can go and not miss this class, because I'm teaching linear algebra during that time. And Thursday is in person, and that is at 12 to 1. This is today, so I'm not saying you guys are screwed. I suppose if you're actually nearby, and this is in person, that's the reason there's cookies today, and it is room 2107. This is in the Learning Commons, and again, but so anyway, there's opportunities for everybody, both classes to engage, although sometimes it's somewhat compromised. Now, I don't know who asked that question, but I think I hope this answers that question, and also reminds you that, the course journal backwards is always here, so that's a place where you can go to look for that. And I am asking whichever student asked that question. I really wish we were in class so I could call you by name, but that just doesn't work here. So I'm going to ask, did I answer your question?
You did. So basically these times never change, right?
This is when Jesse Hayes Carver has scheduled his time and locations and Zoom addresses and all that business.
Okay, thank you.
And for me, it's very useful to have a reverse journal. I mean, sometimes I actually go and look at this. Okay, now, so I'm going to lose this because, wow. I'm going to just minimize this. I'll clean this up later. Okay, so now I'm starting my count again of 10 Mississippi. And Erica, I think you can see the PowerPoint slides again.
I can.
Good. Okay, I'm starting my count again to 10 Mississippi. Okay, your questions, of course, are always welcome, but I hit 10 Mississippi, and so we're going to move on. Okay, and this is just a schedule, and I don't think we need to talk about that. And here is well, actually, here's the question the student asked. So the question at hand was, and by the way, this was in the midst of solving another problem, and we had encountered this integral before. And so I'm not being critical of the student asking the question. I'm just trying to give you the context. So we had hit this integral before, and we hit it again. And the first time we hit it, I said, hey, you're going to see this over and over again, so you might want to know about this. But but it was a Calc 2 lecture. So what I did was I had a step in one of my solutions. So I had this kind of thing. Then I'm wiggling my cursor under, and I went immediately to this, and I said, yeah, and this is the natural logarithm of the absolute value of secant x plus tangent x, end of absolute value plus c. And the student asked a question. He says, well, boy, I don't remember studying that at all in Calc 1, and why is that true? And I did tell the student that, well, one advice I would give a Calc 2 student is to memorize that. And I told the student that at that instant in time, I'm flying this plane. So I said, I'm really not going to go to the whiteboard and work this, but I promise you that I will either make a video or somehow answer your question. So this is the question at hand. Why is this thing equal to this thing? And it is a Calc 1 thing, but that's not a bad thing. I'd be surprised if people didn't need to refresh their Calc 1 stuff. Now, I'm going to start and basically give you, although I'm doing this, I should get rid of that screen sharing thing. I'm doing this rather quickly because you guys are Calc 2 students, but I'm sort of giving you my Calc 1 lecture for this. And actually, what happens is I make it a point to do this problem first when I'm teaching Calc 1 and we're talking about derivatives. So this is, we know a lot about derivatives, but I say, well, and so this is during the derivatives discussion in Calc 1, I say, consider y equals f of x equal the natural logarithm of the secant of x plus the tangent of x. And by the way, the graph of that looks like this, even with the absolute value. So you can see the derivative exists most places. There is a tangent to curve. Now there are places where this goes asymptotic, where it goes up there, and actually it always does that. But most places this is differential, except for some isolated places. So I'm going to say that. And what I'm going to say, what I also say with them is this stands for without loss of generality. I can talk about being greater than 0, but if it's not greater than 0, that means it's less than. It's never 0 because the logarithm is never 0. The domain of the logarithm is never 0. But if it were equal to 0, that's just one of those undefined points. But if it was less than 0, we're using the absolute value, so we make it positive. And so it will be in the domain of the logarithm. So anyway, I just say without loss of generality, let's just talk about the case where this is positive. So I'm assuming that. Now, I do tell them, because it's important for them to know in Calc 1, that, yeah, there's a chain rule going on here. One way to think about the chain rule is to construct this function over here. You're taking x going to secant x plus tangent x, but then secant x plus tangent x is going to the logarithm of the absolute value of that. So this means from a calculus standpoint, you are using the chain rule. So dy dx then is going to be, the derivative you're going to take, it's going to be the derivative of ln of this business. So that is 1 over that business times the derivative of what's inside. Well, the derivative of the secant is known to be the secant x times tangent of x. And the derivative of the tangent of x is known to be the secant squared of x. So from going from here to here, I'm really just, multiplying across, putting this thing in the numerator. So this is the secant squared of x, tangent squared of x, plus secant squared of x, all over secant of x plus tangent of x. And this is dy dx. But if I multiply both sides of this, I have a differential formula. dy is equal to secant of x, tangent of x, plus secant squared of x, all over secant of x plus tangent of x dx. Now, I'm going to ask students who are listening to this to hold this thought right here, because I'm going to refer back to that later. So if you were taking notes or something, you write that down, or, I'm going to be using this. And when I'm teaching Calculus 1 in the derivative units, I would do this, and I'd say, hey, and later on, we're going to look at this again. But anyway, we have that. But now we can talk about the question at hand. So the student, my understanding of the question the student was asking was, well, why is the antiderivative of the secant x dx this business down here? Well, what I'm going to tell them then is, and this is tradecraft, a lot of times in math, what you'll do is you'll add 0 in a clever way. And this time, you're multiplying by 1 in a clever way. And you might say, wow, this is really a clever way. I never would have thought of that. I don't know if I thought of it or not when I was teaching, but I did see it. And I understood the tradecraft that Andre de Corbin, as one math professor, was teaching me. And so what I can do is I just remember it. So you see, Andre de Corbin showed me this tradecraft, and I am showing it to you. So this is something, it should be in your toolkit because it is tradecraft. Okay, so here's what you do. You're multiplying by 1 in a clever way. So you're taking secant of x, and you don't have to think about this as secant of x over 1, but sometimes that's useful for students. I'm multiplying by 1 in a clever way. And the 1 in a clever way is I'm taking secant of x plus tangent of x over secant of x plus tangent of x. And you might say, WTF, that's a real clever thing, but I'm showing you tradecraft. Okay, now when I multiply through then, 1 times this denominator is just secant of x plus tangent of x. So this is secant of x plus tangent of x. But when I distribute the secant up here, I get secant times secant is secant squared of x. And secant x times tangent x is secant x times tangent x. This is all dx. So this thing is sitting here, okay? But now we're going to do a u substitution. And we're going to let u be the bottom, okay? And the bottom is this secant of x plus tangent of x. But then du, we just differentiate this. Now, this is it. Now, I know I called it y probably on the previous slide, but this is your held thought. This is the thought you had. Oh, if y is equal to this thing, then dy was all of this. So you see what I have here is this is u, and this is du. So this is going to be the natural logarithm absolute value of u plus c. And this was an indefinite integral, which means you have to substitute back into the native variable. So doing that, we'll say this is the natural logarithm of the absolute value of secant x plus tangent of x plus c. When I'm saying done here, I guess I'm done with the proof, but I'm also done with keeping my promise. So there it is, the answer to that. You're going to see this again in this class, so I don't know, you probably want to memorize it. Now, I'm not pausing for more questions on that because that's Calculus 1, but we were in the midst of doing trig substitution. And Ericus, I'm going to ask you a question, and it might be a little bit of an unfair question, and I'm not in any sense trying to be unfair. And by the way, I will not think less of you if you say I really can't answer that, but I can't call on anybody else. You and your sister class were pretty much in the same place, but pretty much doesn't mean exactly. So I'm going to go through and sort of talk a little bit about some of this stuff, but very, very, very quickly. And then I'm going to get to a spot where I think it's useful for me to begin talking again. But the question I'm going to ask you, Ericus, is did I pick the right place? And if either and please don't think I will not be angry with you or anything else you say. I can't answer that. That's okay, because I don't grade on attendance. Some students don't show up every day, and all kinds of things happen. But I do want to know from the class because I'm guessing just a little bit here. But anyway, I know we did a bunch of this stuff, and this is about a topic called trigonometric substitution. Okay. So we were talking about integrals that had these forms. And we said there were 3 kinds of things that could happen. And one of them was we talked about, we could have integrals that look like have a squared minus u squared, or the square root of a squared minus u squared in it. And I know we did a bunch of these examples, and the substitution here, this triggers you to think about u equal a sine theta. And you can draw triangles if this is a indefinite integral, and it all will work. And we went through all kinds of things like that. And so we did some examples of that. And the examples are actually in a different place. I'll shuffle the slides differently. I also think we did examples of this. This was one where we were talking about the square root of a squared plus u squared, a different form. And this motivates a trig substitution of u equal a tan theta. It doesn't always work, but it works a lot, and we talked through that. And I also think we talked through this one as well. So here was a problem. I remember doing this problem. So we certainly did that one. And just glancing at this, this is a sign substitution. And we went through the thing of that. I'm going to say, yeah, I suggested you guys, try those kind of things. And I think we talked about this thing that's called example 2 down here as well. Now this ends up being a tangent problem, and we worked through that, and we got that answer. And then I think this actually is another tangent one, although this one was a little bit different. We have, we're raising this we're raising this to a different power. That's okay. You can raise it to a different power. And I think we went through that. And I'm going to pause right here. Did we do this example 4? And Ericus, I'm going to ask you first. And please, it's okay. I will not be angry with you. You say, I really can't answer that for whatever reason. You don't have to explain. But if you can answer that, is this a good place to jump in? Or did I go too far or what?
I think you went one too far, because the last thing I have in my notes is example 2.
Really? Okay.
Yeah.
Well, and by the way, good for you. Okay, so he's saying example 2 is the last thing in these notes. This, I think, was example 2. Let me figure that out. Yeah, that was example 2. Okay, so I'm taking you at your word, and thank you for taking notes and paying attention. That is all good. Okay, so I guess that means we have to talk about this 3. And by the way, I'm not worried about this. If you and your sister class get separated, I can make up those little gap lectures, and we'll stay together. It's all fine. Okay, so this then is where we are. So Ericus, I'm going to take you at your word. It is fine. So we're going from here. Okay, so this is the problem, and I'll make some comments about this. So what is happening here is it's an indefinite integral, so there's going to be a plus c. I'm also going to tell you, when I'm making a trig substitution, drawing the triangle is going to be really important for this problem. And there's going to be a plus c in my answer. And the other thing is, when I see the factor down here of x squared plus 1, that's the same thing as x squared plus 1 squared. That's the same thing as 1 squared plus x squared. So right away I say, a thing to try. My approach immediately is I say, I'm going to try the tangent substitution here. Okay, so anyway, we will go. And now I'm going backward. I will come back to that. But again, the tangent substitution was motivated here. So anytime you see a squared plus u squared, you think about trying u equal a plus tangent, and drawing a triangle can be a good idea. Okay, so that's what we're going to do on this particular problem. And this is the second one that we were doing with the tangent substitution. So we just jump into the work then. Okay. So what we're going to do is we're going to say, x squared plus 1 to the 3/2 is the same thing as this cubed. And so I am doing so here I have, the x squared plus 1 business. And so I am going to do the substitution, x, which is playing the role of u here, is equal to tan theta. Now, when x is equal to tangent theta, that means that the tangent theta is equal to x. And that's the same thing as x over 1. So you see, I can draw my triangle over here immediately. And so there's theta. And so I said the tangent was x over 1. So that is opposite over adjacent. So it is x over 1. But now I have the two legs of a right triangle. And so by Pythagoras, I can find this other one. It is x squared plus 1 squared, square root of that. So this is what I get for the hypotenuse. So I know all 3 sides of this right triangle, and I am going to need that because this is an indefinite integral. So you see I have to return to my native variable at the end of the problem. So I need this triangle for sure. Okay, and now I said that x was equal to tangent theta, so I know that dx is equal to secant squared theta d theta. And that just comes from this and calculus 1. So that is good to go. I have a triangle, so I think I can just substitute in. And so I'm substituting into this thing up here. Okay, so when we do that, what happens is that I'm substituting in. So dx was secant squared theta d theta. Now here I was substituting tan theta, so this is tan squared theta plus 1. But I know that tan squared theta plus 1 is secant squared theta. And this is the square root of secant squared. Well, the square root of secant squared is truly the absolute value of secant, but I'm just going to call it secant. So I get secant in here, and then I cube this. So I get secant squared d theta over, and this becomes secant cubed theta. Okay, so now I am in theta land, so I'm actually integrating this theta. Now I'm going to have to return to my native variable at the end of the problem, but this is the trig substitution helping us out. And you can see, wow, this helps us out an enormous amount, because I have secant squared over secant cubed, so that is going to be 1 over secant theta, and it's still d theta up there. Now, this is one of those things, though, that we learned, and you might remember this was option 5, and this is option 5. We don't know the integral of 1 over secant theta, and this isn't one of those nice little tangent secant kind of things. This is something else. So we'll change everything to sines and cosines, but we know that the secant theta is a reciprocal of the cosine. So 1 over the secant theta is going to be cosine theta. So this is just cosine theta d theta. Wow, what an easy thing to integrate. We know that the antiderivative of the cosine of theta is the sine of theta plus c. So, you know, we basically got an answer, except you don't get full credit if you did this on a test, because you see this was an indefinite integral, so you have to change this back to x. And you might say, well, how am I going to do that? Well, you got this triangle, so here is theta. The sine of theta is going to be the opposite over the hypotenuse, and so this is going to be, so the sine of theta from the triangle is going to be x over the square root of x squared plus 1 plus c, and we are done with this problem. Now I'm going to count to 10 Mississippi in case there are questions on this. Okay, your questions are always welcome, but I reached 10 Mississippi, so I'm moving on right now. Okay, now here is a different problem, okay? And this one's got actually 2 things in it that may be different looking at it. One thing is I have a different factor here. This is u squared minus a squared. Okay, and then I have limits. So this is a definite integral. So this is this problem is different in many ways. Now I don't actually remember exactly what I did, but I'm going back. We'll go to that in a moment. But I'm going to review what happens. Okay, so this was version 3 of this. Okay, so suppose you have the square root of u squared minus a squared. Now this is different. But when you see this pattern, this motivates a different substitution. See, what we really want to have is secant squared minus 1, more or less there. So we're going to let u equal a secant theta. And you see, if you u equal a secant theta, you end up with secant squared. Actually, there's an a factor here, but you end up with the square root of, this is going to be secant squared minus 1 all times a squared, and you can factor the a out. But we do have the absolute value of a that pops out of this, and we're using the fact that the trig identity is secant squared minus 1 is tangent theta. And this business over here, all of this happens because of the absolute value. But you see, so I see this and that triggers, I say, oh, this is the trig substitution that I want to use. So it's pattern recognition, it's trying it, and it's doing a bunch of homework problems, and you get really good at this. Okay, so anyway, this is the substitution you want. But you see, this tells me how to draw a triangle too, because if I divide both sides by a, this says that the secant of theta is equal to u over a. Now here's theta, and the secant is the hypotenuse over the adjacent. It's the reciprocal of the cosine. But I know the hypotenuse, I know this side. So by Pythagorean theorem, I know that this is the square root of u squared minus a squared. And notice that that's exactly what I have up here. So that's kind of how that hangs together. So this is the one that I am using now. Okay, so now I'm going back to where we were. This one. Okay, Now, I'm going to tell you how I, as a mathematician, a practicing mathematician, look at this. Right away, and by the way, I don't necessarily articulate these things in my head. I just have done enough problems. I know these things, but I'm sharing them aloud with you. One thing that certainly comes to mind is, oh, this answer is going to be a number because it's a definite integral. And I see this x squared minus 3. So right away, I am talking about the secant substitution. And another thing that I'm sharing with you is I don't really have to draw a triangle, although I think it is useful because I'm never going to have to reverse the theta discussion. I'm going to use whatever I have for theta to evaluate this integral, and that's the number, and if I did it right, I'm done. So if I want to be barefoot, I don't put my shoes on and then take them off to be barefoot. I just say, hey, I'm barefoot already. And again, that analogy might not be a good analogy, but I'm trying to say how I would approach this problem. Okay, but straight away, I know that this form motivates, I'm doing a secant thing. And by the way, this was u squared minus a squared. And you might say, well, 3 isn't a perfect square. I know that, but 3 is the square root of 3 times the square root of 3. So anyway, here we go. Okay, so with all that stuff, and here is a triangle, except I really don't need it. Let's look down here. You see, we're saying that x, so I'm wiggling my cursor here. So x over the square root of 3 is secant of theta. So I go up here, here's theta. X over the square root of 3 is secant theta in this triangle. So this side over here is the square root of x squared minus 3. No accident. That's what I have up here. So this is a triangle. I'm pretty much not going to use this triangle for this, but I just threw it out there. Oh, I guess a little bit for the heck of it. Okay, so then x is equal to the square root of 3 times secant theta. So I need dx because there's a dx here, and I also need x. So x is going to be the square root of 3 secant theta because that's the substitution that I did. And if I take the differential here, the square root of 3 just sits there. But the derivative of the secant of theta is secant theta tan theta d theta. So this is what I'm going to substitute for up here. And whenever I go to the square root of secant squared minus 3, I'm wiggling my cursor right down here, that's going to be the square root of 3 tan theta. Now, I'm not going through the steps as slowly here because this is Calc 2, and some of those things actually are Calc 1 steps. Now, I'm not trying to be mean, but if you need to blow more rust off your Calc 1 skills, you want to be doing it. Jesse Hayes Carver can help you do that. I can help you do that, and you know, so on and so forth. Okay, so I think we're ready to pound things in here. Now, one thing I haven't done though is I'm changing this from x, and these are the limits on x. You see, if I have a dx, these damn well better be x's, but I'm going to be doing d theta, and I'm going to stop there. So I'm going to have to be changing this to theta values. And the way I change it to theta values is I use this equation right here. Okay, so you see I've got all of this. I know what x is. I know what this is. I know what dx is, so I'm just putting everything in there, and I will be changing the limits because students have to be mindful of the limits. Okay, so if x is the square root of 3, that means that the secant of theta is 1. And when is the secant 1? Well, and the secant's reciprocal of the cosine, so that means theta is equal to 0. So this is your pre-calc 2. This is the trig that you you know, may have to blow the rust off, and really do be blowing the rust off because we're going to be doing a lot of this. Your upper limit when x was 2, the secant theta is 2 over the square root of 3. This actually is a special triangle, so this even would be a good high stakes assessment because you know without a calculator that this is pi over 6. Okay, so let's return to the whole thing then. Okay, so we start putting things in. So this thing right here is the square root of 3 tangent theta. Dx is the square root of 3 secant theta tan theta d theta. And x was the square root of 3 secant theta. And the limits are, because this is a d theta, so these limits are damn well better be thetas. And I will tell you that I'm going to stop. I don't have to go back and plug it in because I made a simplification here. But let's see what happens then with the, now this is algebra inside. Okay, so this square root of 3 in the denominator, square root of 3 times secant theta is going to cancel with the square root of 3 secant theta in the numerator. And now there's only one square root of 3 because I canceled this one, but there's this square root of 3, but there's a tangent theta, d theta left here. So tangent times tangent is tangent squared. So I have the square root of 3. This is the tangent squared theta, d theta. Now, in a previous lesson, we learned how to deal with the tangent squared theta. So you see, this just keeps building upon itself. So that's why it is so important for you guys to strive to keep up. And I know it's hard. It's the summer. We're moving fast. Some people don't have calculus 1 skills and all that, but I'm just telling you what you need to do. Well, so the way we do this integral is we use the trig identity. We're going to call this a secant squared theta minus 1 because the tangent squared theta is secant squared theta minus 1. And I'm going to jerk out the square root of 3 outside of the integral because I told you I'm going to do that 10 times out of 10. Now, the antiderivative of the secant squared is the tangent theta. You learned that from your calculus 1. And then this minus sign is this minus sign. And the integral of 1 d theta is just going to be theta. You add 1 to the exponent divided by the new exponent. You have to evaluate this at pi over 6 and 0. Now, you do have to know this special triangle. This is a 30, 60, 90 right triangle. So we plug those things in. So it is known that this is the square root of 3. The tangent of pi over 6 is going to be 1 over the square root of 3. And if I plug in pi over 6 here, I get pi over 6. And it turns out if you plug the tangent of 0 is 0 and 0 is 0. So that's easy. So you get this. And then what they do, and I think this is a nice thing to do for the final answer, is you distribute here. So root 3 times 1 over root 3 gives you 1. And root 3 times this business is going to be root 3 pi over 6. So this is the final answer. This is what I would expect a student to show me on a final answer on a high stakes assessment. And this actually would be a good high stakes assessment problem. And it's fine. You don't need a calculator to do any of this. And so that's good. Okay, I'm going to pause for a count of 10, Mississippi.
Could you just go over changing the limits from x to theta? This is both root 3 and 2.
Yeah. Okay, over here. Okay. All right. Yeah. And I'm thinking that the best way for me to answer that question, now I need to write this stuff down. Hold on just for a minute. And I'm going to the other, crap, hold on. I do know what I'm doing. It's just I have to press the right buttons here. Okay, and this was x is equal to square root of 3 secant theta. Okay, so now I am going to ending the show, not really ending it, but just, and I am going to answer this question before a break happens. Okay, so I'm going back to Blackboard, but now I'm sharing a blank screen with you. So I'm loading a whiteboard. And you should, Ericus, you should be seeing a whiteboard now, do you?
I do.
Thank you. Okay. So I'm answering this question. Now, I apologize for this, but there's no fixing this. Actually, there is a fix, but the fix involves some work that I haven't done yet. So anyway, this was our substitution. Okay. All right. So now I'm going to say, what happens if x equal the square root of 3? Well, I look up here and I say, if I put a square root of 3 here, that means that secant theta equals, that implies that secant theta is equal to 1. Well, I know that's the reciprocal of cosine. I mean, I don't know how you necessarily do it, but that says that theta is 0. Now, the other one was x equal, I need to look at this, as x equal 2. Now, that means we're putting a 2 here. So that means this implies that the secant of theta, when I solve for that, is equal to, let's see, that is 2 over the square root of 3. But that means that the cosine of theta, you don't have to think about it this way, but this is how I would think about it actually, is square root of 3 over 2. So that means the triangle would look like this. Ah, damn it. I'm going to try to erase this. Bear with me. Okay, so getting rid of that. I'm going to draw a better triangle with this other tool, I guess. Let's see how that works. So here's a triangle. There, that's a piece of a triangle. I will do another piece of a triangle. That's supposed to be the 90-degree angle, and this is the other leg. Okay, so I have that, and so now I know, and this is theta that's in here. I have to go get another thing. This one. Okay, so I'm putting theta there. So you see, the cosine of theta is the square root of 3, and so I have that's the adjacent. So this is the square root of 3 over the hypotenuse, which is 2. That means this has to be a 1. And I know from my special triangles that this is pi over 6. Okay, I'm going to pause here for this one. And I'm going to, in fact, I'm going to cut this out. I know what time it is. Don't worry. I'm still flying the plane. Okay, so we will cut this out and I'll put this back on. You know, I'll make a slide of this. What the heck? And it's not a slide I'm especially proud of with the penmanship, but we'll go back. And so a student asked about that question. I'm just going to stick it here. This is a new slide. I'm going to paste it. You can't see what I'm doing, but that's okay, because we will go back to the, let's see. Okay, so we're going to go back to sharing the application screen. I'll share punch. And we're, Erica, so you are looking at a PowerPoint slide, yes?
Right now it's still that whiteboard screen. I don't know if that's the slide.
Well, I'm changing the slide. Did it
Oh,
change?
now it's PowerPoint.
Yeah. What I did, just so you folks know, is sometimes I annotate things. Somebody asked a question. I thought, oh, maybe somebody cares about that. So I cut it and I pasted it in there. So yeah, I know this is the same thing that was on the whiteboard, but it's really a PowerPoint slide. And there was no way you could have told that. And you did it. You did a good job, you know, dealing with me on that. There's a student out there who asked this question. Your question is answered now. Yes?
Yeah, I got it.
Great, excellent.
Yeah.
Okay, now we are going to take a break pretty soon, but we're going to go along, and I'm going to start my count again. So I'm starting at 1 Mississippi. Okay, well, your questions are always welcome, but I hit 10 Mississippi, so I'm moving on. Okay, and we're going here, and this says, oh, you could change things back. I got to tell you, I don't do that because I don't think it's a good idea. And, oh, okay. Now, what we're going to be doing is another example. This is going to be after the break. But you see, sometimes you have to complete the square in order to use trigonometric substitution. So this is the problem that we're going to solve next time. Now, actually, we're not going to totally solve the problem, but I'll get to the point where you say, oh, I see how I would do this problem. Okay, so that's what we're going to do when we return. And actually, let's see. I probably should have talked about this now. In fact, I am going to talk about this now. I will give you your full break, so don't worry. But I'm getting rid of this first. Okay. So suppose you were confronted with this, and you say, "Boy, I don't know how to do this at all." And I got to tell you what I would think as a practicing mathematician. I would say, well, yeah, this is not u squared minus a squared, but I could turn it into u squared minus a squared by completing the square, which is a pre-calculus thing. So if you complete the square here on this, you get x minus 1 whole squared minus 1 squared. Now you see, if I were to multiply this whole thing out, I would have gotten x squared minus 2x plus 1, but then I'm subtracting 1. So you see, this thing is really the same thing as this, but I use tradecraft to complete the square. Now you might be saying, well, did you help at all here by doing this? Well, yes, this is u squared minus a squared. So this is a secant kind of substitution. And I did draw a triangle. I drew this triangle for your morning class because they wanted to talk about this. So you see what happens here is this is u squared. And so u squared is x minus 1. And that's 1. So I'm saying this, the substitution is x minus 1 is equal to the secant of theta. So that means there's theta. This is the hypotenuse. So the hypotenuse over 1, that's a little bit of tradecraft, is equal to the secant. Now we can use the Pythagorean theorem to compute this other leg, and that's going to be the square root of x minus 1 whole squared minus 1. So you see, I turn this into something that you can do. And I would encourage students to, in fact, try to finish this problem, but that's another piece of tradecraft for you. Now, the last thing is, it turns out if you have studied hyperbolic trigonometric functions, you have other formulas for this. We haven't in this course yet, and I may talk more about this, but I'm considering that one done and this one done. And we are going to do this example 5. That's where we're going to pick it up after the break. Okay, it is 12:16 by my count, Ericus. And so 12:16 is 12:16. That means we will reconvene at 12:26. And we're on break now. We're on break till 12:26. Ericus, Verizon says it is 12:26. Can you see example 5 on your screen?
I can see it, yeah.
Thank you so much. Okay. Now, what and by the way, I mean, this I think is a good example. And the reason it is a good example is because this is a kind of problem that I could and might ask on a high stakes assessment, because you see, it actually requires you to know two things. It says compute the arc length of the graph of y equals f of x equal 1/2 x squared from 0 to 1. So again, that's something that we studied before going along here. But also, in order to compute this integral, you're going to find out that you have to do a trig substitution. So let's talk about that. Okay, so here you have y equals f of x equal 1/2 x squared. But you remember that the formula for the arc length, you have to compute the derivative. So on this chart, I'm just going to talk about the derivative of this. So dy dx is going to be, the 1/2 just sits there, but the derivative of x squared is 2. And then you subtract 1 from the exponent, so this is going to be just x. Okay, so we're going to do that. And so here is f prime of x is equal to x. So f of prime of x is equal to x. And here's the formula for the arc length. So s, the arc length, is equal to the integral from 0 to 1 of, this is the arc length factor, dx. This is the square root of, and of course there is a dy too, but we're doing it dx. So this is the square root of 1 plus f prime of x whole squared dx. But f prime of x was x, so this is the integral from 0 to 1 of the square root of 1 plus x squared dx. Now, right away, students should recognize that, this is going to be a substitution where we're letting x equal tangent of theta because of the form that we have. So this is x equal tangent of theta. And if x equal tangent of theta, I didn't write this here, but if you're taking notes, you may want to write it. If x is equal to the tangent of theta, then dx is equal to the secant squared of theta d theta. And the square root of 1 plus x squared is going to be 1 plus tangent squared, which is going to be the square root of secant squared, which is the absolute value of secant, but from 0 to 1 radians, that's going to be positive. So you see, this thing is going to become secant of theta, and this thing becomes secant squared of theta. So the whole thing becomes secant cubed of theta d theta. Now we have to do the substitution here again, because you see, if I'm integrating d theta, if I'm integrating dx, these limits had better be x's. If I'm integrating d theta, these limits had better be thetas. So I'm going over here, and this is the discussion the one student asked a question about, and we did, but I'm just going to wiggle my chalk over here to talk about it a little bit. So if x is 0, putting 0 here, but if x is 0, the tangent of what is 0? Well, it's 0. So, you know, I know that from my pre-calc 2 at the College of DuPage. And here, x was 1. If x is 1, then the tangent of what will give you 1, and that's the tangent of pi over 4. And you also know that from your pre-calc, and it's not a calculator thing. So you see, we're integrating from 0 to pi over 4, secant cubed theta d theta. Now, we actually calculated this integral before. Don't know if you remembered or not, but this is one of those boomerang problems. And I also told you that we're going to see it again and again and again, and here is one of those agains. And so you encounter this in doing a problem like that. So either you memorized it or you integrate by parts multiple times again, and so on and so forth. But what we end up with, and we learned this, you know, in this class, because we did this calculation in the integration by parts chapter, not chapter, but I don't know, unit. So this is 1/2 secant theta tan theta plus the natural logarithm. Hey, and there's the other one we did, okay? The natural logarithm of secant theta plus tan theta. And you evaluate all this at 0 and pi over 4. Now, you don't need a calculator to do this, because pi over 4 corresponds to 45 degrees. So that's a right triangle that is 1, the square root of 2. So you know what all these things are. So the secant of pi over 2 is 1 over the cosine, and the cosine of pi over 2 is 1 over the square root of 2. So this is the square root of 2 over 1, or square root of 2. The tangent of pi over 4 is 1, as we said, so this becomes the square root of 2. Then we go over here to this next business, and we say, okay, if we put 0 in, oh wait, we're at this business, I'm sorry. So we already found out this, well, we already found this out. So the secant was a square root of 2, and the tangent was 1. So we put all that stuff in, and that is good. But now you say, well, what about the 0? Well, if we put the 0 in, the tangent of 0 is 0, so this is going to be 0 no matter what. And the tangent is also going to be 0 here. But you say, yeah, but this is the natural logarithm of 1. But the natural logarithm of 1 is 0, and so the answer to the problem is this down here, and that's the exact answer to the problem. This would be the answer that I would expect you to tell me on a test. Now notice that this problem involved, oh, you had to know about the arc length and how to compute an integral. That makes it a good problem. There was some question, somebody was asking about the triangle, and I drew the triangle up here, but you see, you don't even have to draw the triangle because this is a definite integral. Okay, I'm going to pause for a count of 10 Mississippi in case somebody wants to ask some questions, and we'll go from there. Okay, I hit 10 Mississippi. Your questions, of course, are always welcome in my office hours. Jesse Hayes Carver's guided study groups, you know, the Learning Commons, you know, your questions are always welcome. But I did hit 10, so we're going to move on and talk about another application. I don't know, there was some reason I put that in there. Now, this example 6, and I did mention to you that I'm working with you know, some other Calculus 2 instructors, because they're saying, hey, let's have exactly the same schedule. And this is a physics problem, and I actually like physics problems. But I do plan to talk about these fluid mechanic problems a little bit in class, but they weren't doing that yet. They said, no, let's do these other chapters first. So I decided, but I decided to throw this in anyway, because this is a real application. When you take a fluid mechanics course or a fluid dynamics course, what will happen is that you will solve problems like this. So my point is not for you to be able to solve this problem yet. Maybe later in this course I will be asking you to solve this problem, but I'm not trying to teach you the physics or engineering of this right now. But my point is to show you that, oh my God, the things that we're talking about actually come up in applications in the middle of application. So to really do your physics or engineering problem, you need to do this. So I'm going to explain this, just what it's about, but I don't really want to talk about any of the physics at all. I'm not trying to teach you the physics now or anything else. All I'm really trying to do is say, yeah, look at this integral in a moment. But anyway, it is a real world problem. It's a problem you'll get in other classes. So a sealed barrel of oil, that's this picture, weighing 48 pounds per cubic foot, is floating in seawater. And the seawater has a weight density of 64 pounds per cubic foot. And here's a picture of this thing floating there. The barrel is not completely full of oil, however. When the barrel is lying on its side, the top 0.2 feet of the barrel is empty. You want to compare the fluid forces against one end of the barrel from the inside and from the outside. Now assume the radius of the barrel is 1 foot and the barrel is lying on its side. The top 0.6 feet of the barrel is above water. You'd have to spend a long time reading that and thinking about it and drawing a picture. Now what we do though, and by the way, that's not going to surprise you, we draw a cross section like we've done before. And a cross section of this is going to be a circle. So I draw so this is again the picture of the barrel, but this is the cross section. So we're slicing through there, and we slice it through there, and this represents all those words. And again, we'll talk about this. We might actually go back and do this problem again, just formulating this. But you see, all of that stuff says you could pick a coordinate system that looks like this. This could be the unit circle x squared plus y squared equals 1. Now, we're not really going to talk about, the physics of all this, but I'm just going to show you, to figure out the force inside that they were asking about, you have to evaluate an integral that looks like this. Which, when you simplify this algebraically, you get this. Well, look at this first integral. This first integral, you have to do a trig substitution. Y is going to be sine of theta. To evaluate this second integral over here, you're going to let, you can do a u substitution here. This is 1 minus y squared, but then there's a y, so the derivative of this du is going to be minus 2 dy, so you can actually compute both of these using things we did in this class. Computing the outside, there's different limits, so you're plugging in different numbers, but you can do this. And by the way, you should be able to do these calculations, and this is engineering problem, so there's calculator, but f inside, if you evaluated this limit here, this integral here, you should get 121.3, and outside is the one down here. You do that. But my point is, wow, you have to do this engineering problem. You have to do the kinds of things that we were just talking about. Okay, I'm deliberately not counting to 10 Mississippi because I'm just saying, hey, those would be good integrals for you to try. And the takeaway of that discussion was, oh yeah, the takeaway of the discussion on those last two problems was you end up doing those things. And so we're finished with trig substitution now, at least from a lecture standpoint. And now we're going into a topic that's called partial fractions. And so the three learning objectives here, and by the way, this is the thing, and damn it, I'm going back. This is the thing that I said earlier. I call this point 1. And part 1, I guess. We're not going to finish this today, I don't think, and I'm not worried about that. We're just fine, but we're wading into this. Now, this is a very powerful technique. And by the way, we study things that sound alike. We studied trigonometric integrals, and then we studied trigonometric substitutions. Those are two different things. and we studied integration by parts, and now we're talking about partial fractions. And so those kind of sound a little bit alike, but they're two different techniques. It really depends on your background. When I teach partial fractions, or when I teach Pre-Calculus 1 at the College of DuPage, partial fraction decomposition is an optional topic. And that means I could teach it or I could not teach it. I actually always teach it. And in fact, it turns out Jesse Hayes Carver took Pre-Calculus 1 with me many years ago. And he has told me since then that he was really glad that I covered that in the Pre-Calculus 1, even though he didn't have to use it until Calculus 2. So this actually could be something that you've studied and forgotten. It could be something you never studied. I'm going to talk about the whole thing. So I'm going to be reviewing the pre-calculus. So we will be talking about that some today. But then we're going to use this because we're going to use this partial fraction decomposition to integrate rational functions. So that's what this whole thing is about. Now, this example is by way of introduction. So this unit examines a procedure for decomposing a rational function, that means a ratio of two polynomials, into a simpler rational function to which you can apply the basic integration formulas. Now, I want to insert here, this can make your life way easier sometimes, and this also is sometimes the only way you can do the problem. And in differential equations, which I teach frequently, you're doing this over and over and over again when you're doing Laplace transforms, which is what electrical engineers do. So anyway, this method is called the method of partial fractions, or sometimes people just say partial fractions. And so to see the benefit, here's an example. We're going to do this problem without partial fractions. And look how much work it is without partial fractions. This is also really a good review of trig substitution that we just talked about. So here is an example of a problem that can be done two different ways. We can do this problem here, the indefinite integral of 1 over x squared minus 5x plus 6 dx. We can do this without partial fractions. So we're going to talk about that. Then we're going to do it with partial fractions. And you're going to see how much easier this problem is to do with partial fractions. And so I think this is a good way to start. Okay, so to find this integral without partial fractions, and you see, me as a mathematician, I would look at this and actually, I'm pretending that I'm a mathematician who has not seen partial fractions. I look at this and I say, well, gee, I wish this was u squared minus a squared, or u squared plus a squared, but it's not. No matter how hard I look at this bottom, I can't make it into either one of those. But if I complete the square, and that's part of your pre-calc kicking in, and again, you know, you can get help with your pre-calc and Jesse Hayes Carver's thing and my guided study groups, or Jesse's guided study groups, my office hours, or you can go to the Learning Commons. They can help you with that. So there's a lot of ways to get help with if you don't remember how to complete the square. But anyway, we're going to complete the square. So we complete the square. So we change this denominator, x squared minus 5x plus 1. We complete the square and we get x minus 5 halves whole squared minus 1 half squared. Now you see, if I were to expand this, I'm just showing it's the same thing. If I were to take x minus 5 halves whole squared, I would be taking x minus 5 halves times x minus 5 halves. That would give me x squared minus 5 halves. But then what I would get here is I would get 25 over 4. It's plus 25 over 4. But then I would be subtracting 1/4. That gives me 6. So you see, this is the same thing, but it looks differently, okay? Now this is of the form u squared minus a squared. So a would be 1/2. And we know that if you got u squared minus a squared, and I know we just finished that lecture, but that, you know, this is the next lecture. So here we can say, oh, or you could say, oh, this is another example. So the u here is x minus 5/2. That's right here, is equal to 1/2 secant theta. That's the substitution we did last time. And that means that x is equal to, I'd add the 5/2 to both sides. So x is equal to 1/2 secant theta plus 5/2. But then I also have a dx here, so I have to do that substitution. So I would say that dx then is the derivative of this. Now the 1/2 just sits there, and the derivative of 5/2 when I throw it on the other side is 0. So dx is equal to 1/2, and the derivative of the secant theta from Calc 1 I know is secant theta tan theta, and this is d theta. Okay, so now you see I'm in really good shape to do the substitution. Now, by the way, one of the things also, oh wow, there isn't a square root here. And whenever we were discussing other things, there was a square root, and you see, oh, gee, this can work without the square root. And you see, when I saw this, I started thinking, oh, u squared minus a squared. So this is going to work. Now, it's not a square root. And so what this is going to happen is you're not taking the square root. This is going to end up being, okay, so this is going to be secant squared. This is going to be, with this assignment, this is going to be 1/2 secant squared theta minus 1/2 squared. And you got a 1/4 there, and secant squared minus 1 is tangent squared. So we get a 1/4 tangent squared here. And then we know that dx is over here. This is dx is 1/2 secant theta tan theta d theta. So I start throwing these things in. Now I do have to draw a triangle because the problem that I'm talking about here is an indefinite integral. So at the end of this problem, you have to change things back to your native variable. So I have to draw the triangle, and so I'm going to look at this. Now, what's going to happen here is if I wanted to know about the secant of theta, I'm wiggling my cursor right where I am, I'm going to multiply both sides by 2. So if I multiply this side by 2, I get secant theta. And on this side, if I multiply by 2, 2 times x is 2x, and 2 times 5 over 2 is 5. So this side becomes, upon multiplication by 2, 2x minus 5. So this says secant theta equal 2x minus 5. Well, here's my right triangle, here's theta. So the secant theta is known to be the hypotenuse divided by the adjacent side. And that's a 1, and so, you know, we know that the secant theta is 2x minus 5, but we put a 1 there. Maybe that's tradecraft. I don't really know. But this secant theta is 2x minus 5 all over 1. But this is a right triangle. That's the hypotenuse. And so we can use the Pythagorean theorem to figure out what is this leg. And if we do all of that calculation, and you see, if you say, if I square this, I will get 4x squared, but the 4 will factor out as a 2, and all this stuff will work out. So you'll get that this is 2, the square root of x squared minus 5x plus 6. Now this part isn't exactly this part, but it's the square root of that. So, you know, this is all going to work. So we do have a triangle, and this will help us change the problem back again into our native variable because it was an indefinite integral. Okay, so let's start examining this then. And I just put dx is 1/2 secant theta tan theta d theta. That's in the top. And in the bottom, I already talked about this, ends up being 1/4. That's just tan squared of theta. But now I'm going to, I don't know, study this just a little bit. So what will happen is that I got tangent, well, first of all, 1/2 over 1/4 is 2. So I'm jerking out the 2. So I have done that. The next thing that I'm going to do is I'm going to observe that tangent theta over tangent squared theta is 1 over tangent theta. So I have a tangent theta in the denominator, and in the numerator I still have secant theta d theta. Now at this point in time, I'm going to say, oh crap, and by the way, I'm saying that you may have to work a little harder with this, but we had a discussion where there were 5 things in the guidelines, and you kind of could go down and you could try them all, although I told you Tradecraft helps you to do that really pretty fast. This is the thing that was guideline 5 in the secant tangent chapter, and so the guideline number 5 said, oh well, if all else fails, change everything to sines and cosines. So if I change secant theta to 1 over cosine, and I canceled one of these tangents already, so that is sine over cosine. So you see I get some cancellation, and what's left when I substitute sines and cosines here is it is 1 over sine. Now 1 over sine is not something you know how to integrate either, but 1 over sine is identical to the cosecant of theta, and so you're really talking about integrating the cosecant of theta. Now, this is real similar to integrating the secant of theta. Now, it ends up being different, of course, but this is something you memorized in Calc 1. And as a Calc 2 student, I'd say, well, if you don't remember it, memorize it again, because you see it came up in a problem here. So there's the 2. This is the natural logarithm of the cosecant of theta minus the cotangent of theta into absolute value plus c. But now, you see, this is theta. My native variable was x, so I have to change this back to theta. So, but thankfully, I drew my triangle over here, so I can go over here and start looking at this. There's theta. This is the triangle. And the cosecant of theta. Now, the cosecant of theta, you have to remember that's the reciprocal of the sine. And so the reciprocal of the sine is going to be the hypotenuse over the opposite. So this is 2x minus 5 over this guy. And there you see I'm writing 2x minus 5 over this guy. Now this minus sign is this minus sign. And then I have to say, oh, I need the cotangent of theta. So I'm going on over here and I'm looking, well, there's theta. So the cotangent of theta is going to be the adjacent over the opposite. So it's going to be 1 over this business, and so that's 1 over this business plus c. Now, there's a whole bunch of simplification that you can do with this, and let's just start talking about the simplification algebra is your friend. These 2 things have the same denominator, don't they? So you see, what you can do is you can do algebra adding those together. And if you add those together, what you will get is now I'm checking the algebra to see. Oh, yes. You will get I'm just going to say you do algebra. I won't have to do all the algebra. But anyway, if you do algebra, you can make it look like this. Another simplification that often happens is if you have a 2 up here, you can bring that up and you can square these guys. And there was a square right there. That makes that prettier. And then what you can do here is you can observe, oh, I got x minus 3 squared in the numerator. And down here, I have an x minus 3 because I now have factored the denominator. So you can, do some cancellation there, and you get the natural logarithm of x minus 3 over x minus 2. And then the logarithm of the quotient is the difference of the logs, so I could get to this problem. Now, if you had questions on what we did, your questions actually are in the previous chapter, because this was a problem where we were doing trig substitution. We're just showing, oh yeah, you could do this by trig substitution, but I spent a long time talking about this. I don't know how many minutes it was, but it was a long time. So this was a hard problem to do this. We're going to do this problem using partial fractions, And you're going to say, wow, this is a much easier problem. So now I'm going to say pretend, and by the way, let's go back and remember the integrand on this problem was 1 over x squared minus 5x plus 6. Okay, now they say, suppose you had observed that 1 over x squared minus 5x plus 6 was in fact 1 over x minus 3 minus 1 over x minus 2. You might say, what? Well, look at this. If I got a common denominator here, it would be this factor times this factor, which would be x squared minus 5x plus 6. Now, if I'm getting a common denominator, I have to multiply on the top and bottom here by x minus 2. And I have to multiply here, top and bottom, by x minus 3. So you see what will happen is here you would have x minus 2. Here we'd have minus x plus 3. If you do all that algebra, you get 1. So you see these two things were the same. Now, the big deal about doing this is the integral you were trying to evaluate. This is 1 over x minus 3 dx. That's a logarithm of the absolute value of x minus 3. And this one is minus the logarithm of x minus 2 absolute value plus c. Now, you might say, well, yeah, Jim, you talked for a while there. Yeah, but I would have done this in let me not talk about me. I'll talk about Jesse Hayes Carver. Jesse Hayes Carver would have done this in 5 seconds. So you see, doing what was a partial and partial fraction was how did I go from this side to this side? And that took a lot shorter even when I was doing it here. And Jesse Hayes Carver would have gone directly to this, and it would have been a 5-second problem. And if I asked something like this, this could be a 5-second problem for you. So this method is clearly preferable to trig substitution, but it means you have to be able to go from this side to this side using partial fraction decomposition. So we're going to talk a little bit about partial fraction decomposition. Okay. I'm trying to think if this is, I'm trying to think of what's really useful. Okay. Now this is the kind of table that's in books and things like that. I'm going to show you what I think is a better table than this. But this is, but there's all kinds of rules here, and it just says, you see, what we're really trying to do is when can we use partial fraction decomposition? And we can use partial fraction decomposition sometimes anyway when we have a numerator, that's why we use n of x, over a denominator. But, and I told you this was good tradecraft, and that's the first statement here. If the degree of the numerator is bigger than or equal to the degree of the denominator, that's what's saying here, do long division of polynomials. Now, some students will say, I don't remember how to do that. That was pre-calc. Well, you learn it again, and you might be thinking, well, Jim, you would never ask us a question like that. I actually often do ask you a question where that is your first step. So review that if that's not in your wheelhouse in your current toolkit. Okay, and when you do that division, then what you get is you get a polynomial which you know how to integrate, plus something where now the degree of the numerator is less than the degree of the denominator, and you can do partial fractions on this. So maybe that's not a 1-step, maybe that's a 0-step, but that's something that we can do. The next thing you do is factor the denominator as much as you possibly can. And so this requires you to review your factoring, and there can be a lot of factoring here. And now this is some real serious pre-calc explaining this. And when I teach this in pre-calc, I spend 2 whole class periods on this. So it's not a trivial thing. and you can remediate this, pretty easily with Jesse Hayes Carver or me or somebody in Learner Commons or some of their remediation materials. But what happens here is the reason that this works is buried in a lot of pre-calc at COD pre-calc theory. And actually, I do talk about this because I want students to understand how come this works. And I think it would be great if you understood how come it works, but just knowing how to work it instead of how come it works might be enough for you to be successful. But if you factor the denominator, it is a fact of algebra that you will get two kinds of factors. You'll get linear factors, and this is a linear factor, px plus q, or linear factors raised to a power, px plus q to the nth power. Or you'll get things that you can't factor, and that means that there are complex roots to this, and so these things won't factor, so you'll get factors that look like quadratics that you can't factor, or quadratics that you can't factor raised to certain powers. And the fancy math term for this is that you have what is called an irreducible quadratic. Okay, so here's what you did then. You divide, if you have to, you factor the denominator. And then for the linear factors, each factor of this generates these terms. The capital A's are constants. And you see here we're talking about if you have p of x plus q all to the nth power. If you have a factor like this in your denominator, you will get all of these terms. You will get a constant a1 over p of x plus q to the first power plus a different constant a2 over p of x plus q whole squared plus dot dot dot, because we're going all the way up to m, plus this is a sub n, another constant, times p of x plus q of x to the m. So you see, wow, this could become quite a calculation in and of itself. Or if you have quadratic factors, so for each factor in the denominator of ax squared plus bx plus c, an irreducible quadratic to the n, you don't get these constants a, but you get other constants and you get x's. So this ends up b1x plus c1 all over this business raised to the 1. And this is a different b2x plus c2, different constants over this business squared plus dot dot dot, thank goodness for dot dot dot, plus this is b sub n x plus c sub n all over ax squared plus bx plus c whole to the n. Now, I got to tell you that, and again, I do spend 2 whole periods in the pre-calculus class, talking about this. I'm not spending 2 periods with you doing it. I know part of it today and part of it next Monday, but I'm showing you a chart now that this is something that I'm telling you the honest truth. Students have told me after the class that this is the best chart I showed them in the entire course. So this thing summarizes all this discussion, except it doesn't say, oh, make sure you divide. But you've got to make that note. And I suppose if I were making this chart again, I say, oh, make sure you divide to start with. But the titles are much simpler. This is actually a much simpler chart. So I'm going over this, and this is easy to remember, and everything else. Okay, so I'm going to talk about it, and I'm using more words, and you may want to annotate your notes here a little bit. Don't know, but for each factor in the denominator of the form ax plus b, that's a linear factor after you factored it, you're going to get a term in the partial fraction decomposition for each factor in the denominator that looks like this. You're going to get a term in the partial fraction decomposition that looks like capital A over ax plus b. For every term that's a power of that, you're going to get a whole bunch of terms. This is the power k, so you're going to get, and these a's are all constants. This is a1 over ax plus b plus a2 over ax plus b whole squared plus dot dot dot. It goes up to ax plus b whole to the k over ak. So you got a lot of terms here. But gee, this thing up here is actually really easy to integrate. And these also are really easy to integrate. You're going to see when we're doing examples. Now, for each factor in your denominator that is an irreducible quadratic form, you cannot factor this over the field of real numbers. You'll get something that looks like this. This is capital AX plus B all over AX squared plus BX plus C. These aren't too bad to integrate either. And if you have this factor of AX squared plus BX plus C whole to the K power, you get a whole bunch of terms that look like this, and they're all different. K equal 1, K goes up to whatever it is. Now, this notes, though, and this is worth noting, you say, oh my God, I have to memorize 4 things in your table. Not really, because you see the first one is the second one when K equal 1. And the fourth one is the third one when K equal 1. So the first and third cases are really special cases of the second and fourth cases, respectively. So as you're studying and memorizing things, this is a good thing to keep in there. But I'm also going to tell you that I, as a practicing mathematician, don't ever look at this table because I know what it says. And if you're doing some good homework and things like that, you'll find yourself in a similar place. Okay, now there are several methods for determining the coefficients for each term, and we'll talk about these in some of the examples that we will do. However, my engineering students love the technique that is called Heavyside's cover-up method. When I teach differential equations and we get to the Laplace transforms, students say, oh, can we use the Heaviside cover-up method? The engineers are really excited about that. And so this is what I'm going to teach you. The first method I'm teaching you, because it's probably the most powerful and easiest method to find some of those coefficients, is called the Heaviside cover-up method. I do know what time it is. I'm flying the plane, but and we're not going to finish this lecture this time. I didn't ever intend to finish this lecture. But this exhibit that I have here is it's really a good treatment of this. This is a PDF that they use in differential equations at MIT, and I just borrowed it. So this is the MIT handout, and I am going to put the full MIT handout into your syllabus tab. Haven't done it yet, and my gosh, might not happen until Friday or sometime, but eventually the Heaviside cover-up method will be there. But I want to do one problem with this Heaviside cover-up method, and I am going to go through this entire little note. And okay, so here is a comment. The cover-up method, or Heaviside cover-up method, can be used to make a partial fraction decomposition of a rational function whenever the denominator can be factored into distinct linear factors. And it can be used whenever that it's more general than this, but that's what we're saying right now. So if you can factor the denominator into distinct linear factors, you can use the Heaviside method. Okay, so let's look at the first example. I do know what time it is. This will be fine. But please pay attention because this is called cover up for a reason. Okay, so here is the thing, and this is pre-calc we're talking about, but that's okay because it makes this integral really easy to do. Okay, so we're looking at this rational expression. And notice that the degree of the numerator is 1 and the degree of the denominator is 2. And I've already factored this for you. What a guy. But I'm just trying to show you the cover-up technique now. So this is factored into distinct linear factors. So that's what we got going on. Now, let's go back to my little table. My little table says, hey, if you have a distinct linear factor, for each distinct linear factor, you're going to get something that looks like this. a constant over that linear factor. That is my first line in that table. That's what we have here because I have distinct linear factors. So that means, according to the theory that I just gave you an overview, I didn't prove it for you because that's pre-calc, but here, that means that, oh, well, this thing then, since the degree of the numerator is less than the degree of the denominator, and I factored this into distinct linear factors, then this thing has to be able to be looked like capital A over the x minus 1 plus capital B over the x minus 2. Now, there's some words here, but I'm not going to read the words for you. I'm just going to tell you how I do it. And I actually do it the same way they're talking about, but with way less words. To figure out what A is, I'm going to say what will make the denominator under A 0. And you might be saying, oh, alarms are going off. The denominator can't be 0. I don't care. I'm asking you that question. What will make that denominator equal to 0? And the answer is 1. So now what you're going to do is go over to the other side, and I'm going to cover up that factor. So I'm covering up what was underneath A. And again, they say cover with your finger. When I do this in a classroom, when we can really do that, I actually put my finger over this. It's not there anymore. And I plug in 1 in here. Well, look what happens when you do 1. It's 1. And by the way, this is covered up. It ain't there anymore. Okay, so this is going to be 1 minus 7 is minus 6. And 1 plus 3, I added it. It's 1 plus 2 is 3. So I'm minus 6 over 3. Minus 6 over 3 is minus 2. That's A. For B. So now we're going to B. Now, and I'm doing the same kind of talk. Okay, so I say, well, what will make the denominator under B 0? Well, when I look at that, I say, well, x would be minus 2. Then I go to the other side and I cover up the factor x plus 2. And I'm going to substitute x equal minus 2. Here we go. Minus 2 minus 7 is minus 9. And minus 2 minus 1 is minus 3. Minus 9 over minus 3 is 3. So you see, B is 3. That was pretty easy. Let's go back and look at the problem that we did as an example way back here. This factors into x, I didn't show the factorization, but this factors into x minus 3 times x minus 2. So I go over here and I'll say, oh, if I plug in x equal 3 and I cover up the factor over here, I will get 1. And if I do the same thing and cover up the other one, I will get minus 1. So that is partial fraction decomposition, and it works that way. Now, I am going to do a count of, let's see. And next time we get together, which I guess will be Monday, although I will be doing math, because a lot of my life is math. Let's see. So what should I say here? Oh, I'm going to say, are there any questions about what I did? And I'm going to talk more about the Heavyside cover-up, and I am going to eventually post this in your notes. But are there any questions about this little example I did to find out that A was minus 2 and that B was 3? So I'm going to count to 10 Mississippi.
Is there another way to figure out A and B?
Sure. If you want to solve 2 equations and 2 unknowns, be my guest. But that will take you a long time. Well, I don't know. You might, some students say they can do all this math in their head, and that's good if you can. But you see, the Heavyside cover-up you actually can do in your head. Yes, there are other ways, and we'll talk about the other ways. But the reason Oliver Heavyside invented this was because it was a lot easier than solving 2 equations and 2 unknowns. Now, if you like to solve 2 equations and 2 unknowns, but realize you're not doing that with a calculator, you're doing anything you're doing by hand. And so I think you're going to find, and by the way, maybe it sounds like I'm being rude. No, I'm not trying to be rude at all. I'm just saying for problems where this applies, it's way quicker than the other ways. But the answer to the straight up question you ask is there another way to do this? Yes. And in fact, since you asked that, what I'm going to do is I'll talk about how you could do that this way. Now I'm trying to answer your question as well as I can. So how would you do that? Well, okay, you would say, well, here's a common denominator, so you would get a common denominator over here. So you say, well, the common denominator over here is going to be x minus 1 times x plus 2. So you're going to multiply top and bottom here by ax plus 2. And then you're going to multiply top and bottom over here by bx minus 1. And then what you're going to do is you're going to simplify that algebraically. And then you're going to equate the coefficients that you have. So you'll have one system of linear equations that's going to give you 1, and another system of linear equations that's going to give you minus 7. And so you can say, well, I will solve those just 2 systems of linear equations for A and B, and I'll know what A and B are. And there are very few people who would rather do that than the Heavyside cover-up thing. Now, and by the way, if you say, well, I really kind of like doing that, you will have an opportunity to do that because Heavyside cover-up doesn't always work, but it works in a lot of cases, and so it's a good thing. So my answer is, sure, there's another way to do it. The tradecraft I would recommend is, hey, it would be useful if you knew how to do this way for the problems and the coefficients that you can do. Okay, thank you for all your questions, and thank Ericus for all of his support. That is really useful. And God bless you guys, and young people should be careful over the weekend. I'm stopping the recording now, and